exercise doing lessons class.
Sit, fetal position, rising action, climax, falling action, and rusting structure.
Very good. All right. Now let's pick it up where we left off on the handout. And just in case you're curious, if I can dust through this today, we'll see how the speed goes. Next time we'll be heading into lab, and we'll start teaching you how to run all the equipment over there. 1, 3.
Do we need shoes?
Yeah, I was just about to say. Let me run down the rules on the lab. In here, nobody cares. Over there, the engineer cares a lot. You have to wear closed-toed shoes. Tennis shoes, anything will do. Rubber slippers will not do. So if you look down, you can see your feet. You can't do it. Now, we talked about squeezing electrons through a thinner wire, and in doing so, causing the filament inside to heat up. And if it heats up enough, then it starts glowing. It won't catch on fire because they sucked all the oxygen out. You can't have a fire without oxygen. And so it will glow and glow and glow and get brighter and brighter and brighter. Now, is it possible to burn that filament out? Yes, of course. Over time, they get more and more fragile. When they're hot, it's really easy. If you just pink like that, you can break the filament. I'm sure you've discovered that in your home. So you want to be a little bit careful with the bulbs. We're going to cover some safety rules with the lighting instruments that are inside the studio, but there's only 2 things that you really need to worry about here. One of them is never touch bare glass with your fingers. If you do, the oil from your hands, no matter how clean they are, the oil that keeps your skin from cracking will get on the glass. It'll create a soft spot where that oil is, and then the bulb will just continue to expand until it explodes at that weak point. Some of you may do a blister on a tire, on a car, same thing, exactly the same thing. And then when it explodes, shards of glass fly out, and of course usually lights are pointed toward talent, so you probably don't really want to blind your talent by shooting shards of glass in their eyes. Bad idea. Hard to get people to work for you like that. Okay. Need to talk about magnetism, which is the next thing down on your sheet.
Yeah, magnets. How do they work?
Magnetism, like lightning, occurs naturally in nature. There is a mineral called magnetite, and the Chinese are credited with finding it, or the Greeks. Big controversy there as to who first came up with it. But you'll notice it says the ancient Greeks nailed it by naming a city Magnesia. Well, okay. Sounds to me like they won the race. But anyway, this is chunks of iron ore probably struck by lightning. What does that do? Well, we'll talk about that in a minute. However, it was found that it would attract iron. And that led to the development of the compass. How does this work, really?
Magnets. How do they work?
It's kind of hard to explain verbally. So it's much easier if I can actually do a demo and show you. The next paragraph is kind of important. The magnetic compass soon spread to Europe. Columbus used it when he crossed the Atlantic Ocean, noting not only the needle deviated slightly from exact north, true north, but also the deviation changed during the voyage. Around 1600, William Gilbert, positioned to Queen Elizabeth, posed an explanation. The Earth itself was a huge magnet, with its magnetic pole some distance away from its geographic lines. They're pretty close, but they're not right on top of each other, as any ship pilot or airline pilot can tell you. There is always on every map true north and magnetic north. And every map will show you the deviation of how much it's off. In Hawaii, it's about 7 degrees. How do I know that? Former Boy Scout. Okay, so what is magnetism? Oh, we have a North Pole and a South Pole, right? Yes. Top of the planet, bottom of the planet. Next page. Until 1821, which is a hell of a long time from the time the Greeks and or Chinese found this to then, only one kind of magnetism was known, and that was the one that pretty much showed up in magnets, and most of those in nature. You can make a magnet, but it takes a bit of understanding to do it. Then a guy named Oersted, he was Danish, was showing the flow of electric current in a wire, and noticed that the current caused a nearby compass needle to move. So electrons moving through a wire can move a compass needle. There must be some relationship there. Has to be. So, the new phenomenon was studied in France by André Marie Ampère. That should look familiar. Amps was named after André, who concluded that the nature of magnetism was quite different from what everyone had guessed. It was basically a force between electric currents, two parallel currents in the same direction attract and the opposite direction repel. Iron magnets are a very special case where Ampere was also able to explain that. Now, what Van Oersted actually saw. In nature, magnetic fields are produced in the rarefied gases of space, in the glowing heat of sunspots, and in the molten core of the Earth. Such magnetism must be produced by electric currents. Finding out how those currents are produced still yet is a mystery. Don't know. Now, we know they're there. We can make use of them. We can find them. We can sort of demo all around them, but we can't actually have you see them. Next thing down. Michael Faraday, credited with fundamental discovery, also proposed a widely used method for visualizing magnetic fields. Here we go. Remember, I told you can't really see with your eyes, but we can demo that it's there. All right. Imagine a compass needle freely suspended in 3 dimensions near a magnet or an electrical current. You can trace in space, in our imagination anyway, the lines one obtains when one follows the direction of the compass needle. Faraday called them lines of force, but the term field lines is now in common use. And there on the right, that darker picture, that's a photograph of it. Now, compass needles and field lines. And notice that picture on the left of the Earth's North Pole and South Pole. Field lines of a bar magnet are commonly illustrated by iron filings sprinkled on a sheet of paper held over a magnet. Similarly, field lines of Earth start near the South Pole, curve around in space, and then converge again near the North Pole. A magnetized bar has its power concentrated at 2 ends, and they are polar opposites, so they're called the poles. They're known as the North Pole and the South Pole, just like the planet. Because if the bar is hung by its middle from a string, its north end will point north, and the south end will point to the South Pole. The end will repel any other north ends, and the south will repel any other south ends. But north and south have a strong attraction to each other. The region where this is observed is called the magnetic. Okay, here we go. Either pole can attract iron objects such as pins, paper clips, and so on. This is because under the influence of a nearby magnet, each pin or paper clip itself becomes a temporary magnet. Its poles actually rearrange in a way appropriate to magnetic attraction. How the hell does this really work? Hunk of iron. All you do to make that hunk of iron into a magnet is rearrange the electrons to go in one direction. That's all. Now, those of you that are carpenters, you worked in construction and so on. If you have a hammer and you're pounding nails, and the nails have an iron component, they're not aluminum or something, iron component. Over a period of time, the head of your hammer will become magnetized. You probably have observed this. So you can pick up nails with the head of the hammer over time. How's that possible? Because you keep pounding it, and physically, after so much pounding, you start rearranging those electrons. Takes a long time though. It's not a good way to make a magnet. Yeah. Screwdriver, same thing. Only with a screwdriver is usually a real pain in the butt. Because then it picks up everything. Oh, by the way, the bubbles on the light bulbs, it's where somebody touched it. And you can figure out why. They probably pulled it out like that. And right where they touched it, look where the bulb is. I caught this one before it exploded. Another one. That's supposed to be dead straight. One more. Okay. Now, we need a piece of paper. I'd rather have a piece of your paper so you don't think that I'm doing a magic trick. Here's a piece of paper. Thank you. Gather round. All right. By the way, you're wondering where the hell all this is going. It's going toward electricity. Now, let's talk about these electrons. I mean, we've talked all about them, but you haven't really seen them. So, top of page 6, where it says it's all related to electricity. Matter, that means everything, consists of electrically charged particles. Each atom consists of light, which is, of course, a photon. Negative electrons swimming around a positive nucleus. Now, we don't bother calling them negative electrons, we just call them electrons. The assumption being all electrons are negative. Objects with some extra electrons are negatively charged because they got extra electrons, and electrons are negative. Therefore, they're negatively charged. Duh. While those missing some electrons that aren't balanced out and stable are positive. If they were stable, you couldn't have a flow between the negative and the positive, could ya? It would be like the two water tanks. They're stabilized. No flow. No electricity. Such charging with static electricity happens sometimes when objects are brushed with cloth or fur on a dry day. I can't show you that because in Hawaii we don't have any dry days. Our humidity never drops below 50%, so I can't demo that for you. Actually, it's rare that our humidity drops below 72%. Experiments in the 1700s have shown that positive repels, positive, negative repels. Now, close to 1800, it was found that when the ends of a chemical battery were connected by a metal wire, a steady stream of electronic charges, or electrical charges, flowed in the wire and heated it up a little bit. That flow became known as current. Jot that down. The flow is current. If you don't have a flow, there is no current. They just sit there. In a simplified view, what happens is the electrons hop from one atom to the other in metal. So, if we did have that periodic table of elements up here, which you've all seen, I'm sure, in most classrooms, this is why gold and copper transfer electricity so well. Both of them have this need for extra electrons. So they're willing to pass that electron right on down the line because they'd like to have it. They're not quite. balance. Gold and copper is normally what we use because of the expense, almost always copper. It has only recently, by the way, in the last 10 years, become a fact that copper is worth stealing. This is why every now and then you hear somebody getting arrested for trying to sell copper wire that they sold out of the freeway lighting fixtures and all that jazz. Prior to that, copper was the cheapest metal, really, that almost you can find in nature. That's why a penny's made out of copper. It's virtually worthless. Really, 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 really cheap. It does a couple things well, though. It conducts heat well, which is why your best chef pans are made out of copper, and electricity very well. So now, the cost per pound of copper, because they pretty much stopped mining it, we're just about run out, the cost has gone way up. So now it's worth stealing to try and resell it. People melt it down, things like stuff. Okay, so that's what's going on within the atoms. Now, big controversy here. I don't think I have one of those to show you, but somebody stole it from me, damn it. Unless they put it back. Now it's gone. But I can talk you through it because I'm sure you've seen it. On somebody's desk that has way too much to do, or way too little to do, actually, they have a frame, and then suspended on the frame are balls. Have you seen this? You take one ball, you pull it back, and you let go, and it goes bang, 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 and the last ball moves. If you pull two of them back and let go, these two will move together. Three, pull these three back, and this one, and if there were two more, would move. So it's kind of a continuation of the motion. If you just pull one ball will move, pull two, and the other two will move. Let go, and it goes clink, 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 and that's the way. Some folks think that's how electrons move through a wire. Other folks think we're banging into each other. Other folks think, no, there's an actual chemical transfer of the electrons from atom to atom to atom to atom to atom. Which one is right? Jury's still out. Since you can't see it, it's kind of hard to prove it. Okay, so now we know what a current is. Back to Ørsted in Denmark. We can move that compass needle around so an electrical current therefore produces a magnetic force. When you want it, it's great. When you don't want it, we call it interference. You listen to the radio and somebody turns on the microwave. That's when you don't want it. Okay. Now, go to page 7. Two circular currents attract each other. Two circular currents going in the opposite direction will repel. This is how you make a motor, folks. Now, I want you to, I don't have time in class to go through the next part, but I want you to read it on your own. It has to do with coils and more than 10,000 turns on each coil, and why you need that many and why that's important to create an electromagnet. We don't really use electromagnets that much in television production, but we sure as hell use motors and a whole bunch of other stuff. So read that one on your own about coils and how you can actually increase the amount of voltage by the coils. Now, what about AC electricity? All right, now we're going to get into something that is manufactured. Go to page 8. We know for a fact. We know for a fact that when that current flows, that there's a magnetic field around it. Therefore, if we create a magnetic field and break it, we ought to be able to do just the opposite and make a current. Yeah? So we're going to do that now. A very strong magnet. North pole, south. The other end of the magnet with this south or north. And here comes the important part. AC power now, not DC, okay? It says AC, don't get confused. AC stands for alternating current. What the hell is alternating? Remember, DC stands for direct current. If DC stands for direct current, and the electrons in DC flow from negative to positive, then if alternating current is different, what might be alternating? Instead of going from negative to positive all the time, maybe it's going negative, positive, positive, negative, negative, positive, positive, negative. That's what's alternating in our alternating. So as I spin this, it's going one way, the electrons are flowing one way, and then when it gets to the other pole, they're going back the other way. If I had a oscilloscope hooked up to that rather than a light bulb, it would look something like this. When it's at rest, it's zero. No movement, no current. Then it goes up to a positive, up as it's flipping through the south pole. Comes back down here to the zero line, and it doesn't actually stop. Back down here, and here's your zero line, so there's no pole. Comes back down here. Now, from this point to that point is called a cycle. Cycle. Here to here. That is a cycle. Because it's cycling through, going up to a positive, back to zero, when we flip it the other way, and then down to a negative. Then back to zero again. That's what's alternating. So in the United States of America, when we refer to our electricity, we say AC, which is alternating current. And then we'd like to know maybe how much. What's the first page of your handout that's the answer to how much? Nope.
Amps.
Volume, how much? 120. What do I put here? Yeah. Go to your first page on the table.
Watts.
What's the pressure? The pressure. Yeah, volts. That's the pressure. And then it dips to a minus 100 volts, back up to zero. We start the cycle all over again with the next cycle. So what we're alternating here, unlike direct current, which flows only from negative electrons to positive electrons, what we're alternating here is the flow of electrons from positive to zero to negative to zero. We are alternating that flow. Not having it flow in a direct pattern of negative to positive, but alternating it from negative to positive to negative, flipping it backwards again. Okay? Now how do we know that this is true? You can see it. take a pencil or your hand, either one. Put that object between you and the nearest light fixture. Do it. And move it as fast as you can. No, that's way too slow. That fast. Really fast. What do you see?
Blur.
What you should see is something that looks like a shadow. Look again. See a shadow in between? Yeah. That's because that light is going on and off. And your hand is moving faster than the on and off side. So you have strobed it to freeze your hand. Now the question is, we know how much. The question is, how fast is that?
30 miles per hour.
We have 120 volts AC, but we also have 60 cycles. That's 60 cycles per second. See, cycles doesn't mean anything unless you put it against the time. Miles per hour, same thing. Cycles per second. How often is this happening in 1 second? The answer, Professor Bob, is 60. 60 times per second. If we were just measuring half a cycle, what's the math? 30. So this would be 60. This here, from here to here, would be 30. Cycles per second is a mouthful. So there's some shorthand on this, and some people call that CPS, or cycles per second. Some people call this Hertz, H-E-R-T-Z, named after the Austrian guy who did a lot of work on this. Hertz. So you can call this phenomenon here cycles per second, or CPS, or you can call it Hertz, or you can call it what most engineers call it, HC, which is even shorter, for the abbreviation for Mr. Hertz, HC. All of them mean cycles per second. Now I know what you're thinking. This is very academic and esoteric. Who would have thought? Well, you should think. How many of you play guitar or ukulele? Which way does your string go? Up or down? When you pluck it, does the string go only up or only down? It does both. Look familiar? That's what's happening to the string on your guitar. That's what's happening to my vocal cords. That's what's happening to the strings in the piano. That's what's happening to your lips when you play a trumpet. How fast is something vibrating per second? Now, the vibrations mean nothing unless you put a measurement, the per seconds part in. Just like miles means nothing if you're trying to measure speed if you don't have some other number with it. Miles per hour. Light years. The distance light travels in 1 year. Light years. Miles per hour. Cycles per second. Now, those of you that play piano ought to know this. Piano players, raise your hand. Nobody plays piano?
I can sound good for sure.
Okay. Well, have you had lessons?
I've had a few.
Okay. Piano tuner comes to your house. Time to tune the piano. And the problem is with the humidity we have in Hawaii, the wood inside warps all the time. So you got to tune it maybe twice a year. Have it down, be in tune. How often do you have to tune your guitar? Every time. what are they tuning it to?
So,
24 to 55 gigs.
There's strings inside on the piano. So, your piano tuner person usually comes with some tuning forks and strikes them with a mallet. You can hear that. You can hear it even better if I put it on something that will conduct the sound. Watch. Hear the note? Here, right there. That note, that vibration, is a certain number of cycles per second. How many?
480.
480. That's what the numbers mean. So we're going to pretend this isn't 480. We're going to pretend that this is the musical note A, which is what most people tune to, because it's right in the middle. The number of cycles per second that we all refer to as the musical note A equals, come on, really impress me. Anybody know? How many? 480. What? 480. No.
24.
Center A is 440 cycles per second. This is a long, here's the one that was close to A. Here's a much longer one. So it can't vibrate as fast. This one can't vibrate as fast as the shorter one. The shorter one doesn't have a lot of mass, so it can move fast. This has a lot of mass, can't move as fast. Thick guitar string, thin guitar string. Hear the note? See the other one. Higher. So, how many vibrations per second on this one? 256 cycles per second. This is a low C on a piano. That's how important cycles per second are. You wouldn't have music without it. Now back to your first page. So that's the push. That's the push, the volts. What about the volume? What about the gallons per hour? What about the quantity? We know that's the cycles per second. Quantity is what you would refer to in music as the volume. The quantity for electricity is preset at a level that you can't kill yourself right away. So in a room like this, industrial, and mostly now in homes, the maximum carrying capacity of one circuit is usually 18 ohms or amps. Now let's stick with the right terminology here. Ohms is a little bit complicated, so let's just say amps for now. That's how much. It's the pressure, that's how much. So in that circuit, we've got 120 volts alternating current running at 60 cycles per second with about 18 amps of power available to us in that circuit. What would happen if you plugged 19 amps of stuff into that circuit? It would blow up. It would either catch on fire or the circuit breaker would break and break the circuit so that you can't catch on fire. So, that is electricity. Remember that the amps is the volume or how much, and that's what kills you. If you were in France, how many volts would you have?
40?
Well, let me back up. How many of you have traveled to Europe? What happens when you plug anything that you brought along with you, like a shaver, hair dryer, or radio, anything, into a European circuit? What happens?
Fry it.
A little cloud of blue smoke comes up from the device that you just burned up. In all of Europe, they have 220 volts. I'd write this down if I were you. 220 volts. And they don't run at 60 cycles per second. They produce their electricity at 50 cycles per second.
240 volts?
220. They can go to 240. Just like 120 can go up to 140. There's some variations. But if you look it up, what you will find in Europe is 220 volts alternating current. They have alternating current. But at 50 cycles per second. So it's being produced slower. That's why if you had a television, and even if you had an adapter for the power, it would flip. Because the recorded image is at 60 cycles per second. You're playing it back at 50. It's going to flip. Just like your fingers. So it's important to know what country you're in. Now, by the way, since there's so much commerce between Hawaii and Japan, what is the voltage in Japan? 120. Same. That's why it's really cool that all the Japanese stuff, all their electronic components work just fine in the U.S. because that's where they're made to work. So you're doing just fine with 100.
Switch.
The problem with the 50 cycles is if you have anything with a motor in it, anything, because the cycles per second are slower, the motor is running slower, it cannot self-cool, and it just goes up in a cloud of smoke, burns up. So you plug your hairdryer in, it'll go zzz, and it will catch on fire. Yeah.
Did Japan switch? Because I have a lot of old Japanese that runs that one.
There are some places in Japan that actually run 50 cycles per second.
100 volts.
At 100 volts. They have a big problem in getting their power out of the country. That's why they went to nuclear power way early, pretty much before anybody else. And if you notice where those plants are, they're way out. That's not just for public safety. That's to get the power to where the most remote areas are. So Japan is somewhat unique, but we're not in Japan. Let's stick with the United States. So that's what you guys got to deal with. Now, earlier on in history, the building codes in Hawaii and everywhere else, it wasn't 18 amps available to use, much less. It was usually 12 or 14 amps. The reason was the wires in the house were thinner. Because back in the 40s, 50s, and 60s, we just didn't have that many appliances. If you had a house, maybe in your living room you might have a TV and a radio. Maybe in the kitchen you might have a stove which is running on its own circuit, and a refrigerator which is running on its own Maybe a toaster you plug in. You got to get no microwaves, no none of that shit. So we didn't have no dishwasher, certainly. So we didn't have all these appliances that we have today. Hence the need for a whole lot more amps was lower. Why put in more than you need? So because wire's expensive, so they put in enough wire to handle 12 or 14 amps comfortably. So older houses will have much lower amp rating, which makes them a little dangerous for this reason. If you're working in an old office building, like downtown, you gotta go do a shoot downtown, you wanna be careful to find out what are the amps per circuit, because if they are 12 or 14 in an old historical building downtown, or maybe out in Hawaii Kai, one of those old homes out there, or Kaneohe, and they only have 14 amps available, that means that's all you can run, and if you go above that, there's a good likelihood that you can burn the house down. Here's how. Back in the old days, when 14 amps was the maximum standard, what happens if you plug something in that pulls more than those 14 amps? Let's say you have a short circuit by accident. They had what was called a fuse box. And in the fuse box were a whole bunch of fuses. And then the power would come out the other side. What's in a fuse? Same thing that you have in your car, by the way. It's exactly the same. So if your radio goes out in your car, it's probably a fuse. Inside each one of these things was a glass filament. I mean a filament inside glass, sorry. And very thin wire. Really thin wire. And then the power would go out the other side. The idea here was, we know that electricity causes friction. Toaster, light bulb. If too much electricity, like in a short circuit, is flowing through, the idea was, it'll get so hot in this little wire that it will very quickly melt, break the circuit, and then these thicker wires will heat up because we killed the circuit, stopped the flow. That's a fuse. Problem is, sometimes you do a lot of damage while that wire is getting hot enough to melt. Now usually it's pretty fast. Old style fuses were about 1/10 of a second. So it's pretty fast. But here's why this time of the year, if you turn on your TV, you're going to hear about people's houses burning down on the East Coast. Because West Coast is new, East Coast, old houses. In the fuse box downstairs, it just so happens that the diameter of these fuses, which you screwed in like a light bulb circuit, the diameter is exactly the same size as a U.S. penny. What's a penny made out of? Copper. So if in the middle of the night your furnace, your electric furnace, overheated, started pulling too many amps, and hit the fuse melts, but now it's 2 o'clock in the morning and it's minus 10 degrees Fahrenheit. And you forgot to go buy fuses at the hardware store. People would find a penny, use their thumb, screw it into the fuse hole, and now the circuit would become whole again, the power would come back on again, but effectively what you did was that. So now the current can flow freely, and whatever melted that wire in the first place is still doing it. So you're passing more and more and more and more power through that penny to the point where the wires start glowing, melt the insulation, and burn your damn house down. Where are the wires? Where are the wires in here? Well, there's a switch back there. Do you see any wires? Where do you think the wires are that go to that switch?
Inside the wall.
They're between the walls. In Hawaii, mostly we have single wall construction, But back east, where it's cold, they have double wall construction. There's all kinds of stuff between the two walls, between the interior and the exterior wall. You have insulation, you've got wiring, you've got plumbing, you go on and on and on and on and on and on and on. Okay? Well, all that stuff is now wrapped around the wires that are between the walls. The wires heat up, start glowing red, catch on fire, whatever's there, including the drywall itself. And all of a sudden you got a fire that you have no idea is happening because it's behind the wall. And then it goes right straight up to the second floor, right straight up to the third floor, through the double wall. And by the time you smell any smoke, your house is already deeply engulfed in flame. This is why people get killed in house fires. How can you die in a house fire? You smell it, run out. That's house. So, go to page 9. Look at that little drawing of the little electrons there, where it says electricity goes one way when you plug something into a wall plug, AC now. Notice all the little negative electrons are heading toward the right, heading toward the filament. Go through the filament, and then notice they're coming back again to complete the circuit on the lower side. So they go one way, then back the other way. When you flip the alternating current, look, now the negatives go the other way, and the positives take their place. So here we're not dealing with one direction of the negatives always flowing toward the positives. Here we're dealing with the negatives going one way for half the cycle, and then the negatives going the other way for the other half of the cycle. Take a look at page 9, bottom, and you can see how here they spin the magnets and the wires remain stationary. Just the opposite of what I demoed for you with my little machine. Graphically, page 10. Take a look, alternating current now, and there's the machine that I just used. Notice that it's being cranked to the right, so we're getting a positive 1 volt here. It goes back to 0 whenever we're not breaking the north-south pole. And then I keep cranking, and now it's breaking the south pole lines of flux, and so we get a negative 1 volt. So what's the deal? Well, this is where Edison and Tesla had a big fight. Edison had invested everything in direct current. And he found a way of creating direct current, generating direct current, not through batteries. No. Tesla said this is extraordinarily dangerous. If you touch that circuit, because the electrons are going one way, it will freeze all the muscles in your heart and so on, because there's no let up. Here, it's going, you got a chance to live. But not with direct current. The other big problem with direct current was it was great for big cities like New York because it would hold a lot of power for a short distance. But as you increase the transmission distance out into the boonies, the power would drop off. Where was it dropping off to? It's dropping off into the wires. The wires themselves were resisting that free flow. And the longer you went, the longer the wire, the more resistance. I think of them as stones in a stream. The more rocks you have in the stream, the less water is going to be able to pass, right? And so that's what happened with DC power. They got into huge patent battles. At one point, Tesla actually worked for Edison at General Electric. Edison, to his dying day, felt DC was the right way to go. And then economically turned out you couldn't transmit it more than, I think it was like 8 miles or something. So AC power won. The World's Fair was wired for AC power, and that was the end of DC for using power for mainstream stuff in the United States. One of the big holdbacks and the reasons that Edison felt that DC was the way to go was It's much cheaper and easier to build a DC motor than an AC motor. AC motor is pretty complicated. DC motor is very straightforward, easy. That's why the starter motor in your car is run off 12 volts DC. Much easier. Anyway, AC power 1, and that's what we've got to deal with. Now, I want you to, as best as you can, try and remember all the stuff that I talked about. Transformers is next. Again, I'm not going to have time in class to cover transformers, but it also has to do with the number of coils we wire. This time on a magnet. You load it up on one side with secondary coils, half as many on the primary coils, and you can change the voltage from 120 to 220, or vice versa. And that's how it's done. Take a look at page 11, shows you exactly how it's done. This all seems like magic. It's not. It's just pure, simple physics. Now, what I want you to walk away from is all of these numbers, and most importantly, for the rest of TV production, 60 cycles per second. Because that's how fast a video camera makes a picture. Can't go faster than that because it's going on and on. Can't go slower than that because then you have big gaps between each picture. So all of our production equipment, editing equipment, cameras, everything else is based on that 60 cycles per second and hitting that number exactly. Not 59 and a half, but 60. And so we'll pick it up there with the next lecture, and I'll explain to you why that's so damn critical with interlaced photography, linear photography versus progressive scanning. But for now, remember all of this stuff. Cycles per second in hertz, how often something's vibrating per second. And those of you that do have a guitar, ukulele, piano, pluck the strings and see which way they're going. You'll see that it's doing that. Okay? Same. Of course, drum hits going up and down, which works exactly, by the way.
Oh, yeah.
Okay, guys, that's it for today. Don't forget, closed-toed shoes next time. Mandatory. If you ain't got them, you can't come into labs. You're going to get an empty lab that way. Wear your shoes then.
I need to use the bathroom.
But you're in.
Yeah, I'll have to move in, so that's my friend works across.
30?
That's a lot.
Oh, word. Yeah, so I'll send it to you guys.
I'll just make a new group.
This.
For sure.
This. A half
Sounds good.
You
Sounds good.
Tomorrow.
This. So when you're working with interlaced video, you have to
Tomorrow
have
is a
this
PS101.
half
I don't know what that is.
and this half cycle. So this runs at half that amount.
Cool. I'll see you tomorrow.
So when you add the two together, you got 60. So the question is, what's the cycles per second for a half frame, which is called field? The answer is 30. So you'll be able to see it on an oscilloscope. I'll actually be able to show it to you. That's why, if you're used to production on an oscilloscope, that's why you have two trays. One's from the left side, one's from the right side.
The 60 cycles, you said it's going to be important. Is that because of the frames per second?
Yes.
Got it. Kind of had a feeling that's where it was going.
That's part of it. That's